Hey everyone, this is Dr. Habib Ahmed. Welcome back to my channel after a break of a couple of months. I was actually extremely busy in my job transition. I currently work at Georgia Institute of Technology. Over the last couple of months, a lot of people requested me to post a video on the Silvaco TCAD simulation of triple junction solar cells. The good news is that I worked on it. Today we will explore the Silvaco TCAD simulation of triple junction solar cells. These are advanced solar cells designed to capture more sunlight and produce higher efficiency. They are used in satellites, space missions, and concentrated solar power systems. Triple junction solar cells are special because they use multiple layers to absorb different parts of the sunlight. As you can see over here in this structure, we have got 17 different layers. And you can see over here we've got cell number 1 based on indium gallium phosphide, cell number 2 based on gallium arsenide, and cell number 3 based on indium gallium arsenide. And further you can add another layer over here after a tunnel junction of germanium as well. And that is going to further enhance the performance of this solar cell, and it's going to make it 4-junction solar cell. Well, triple junction solar cells achieve higher efficiency, but their performance depends on current matching. Each layer is connected in series, and the cell with the lowest current limits the total performance of the solar cell. So getting the currents of all layers to match is tricky, and also it's very important for high efficiency of the solar cell. It takes a lot of iterations. It's not an easy process. I have performed a Silvaco TCAD simulation of triple junction solar cell achieving efficiency of 31.5%. It was not easy. It required fine tuning of the thickness, doping concentration, and it also required bandgap engineering of the individual layers by varying the content in ternary alloys especially. And to give you an idea how difficult the process is and how time demanding this process is, let me show you the folder where I performed, I've saved different codes for the Silvaco TCAD simulation. So here in this folder you can see I've got like 131 different iterations for the Silvaco TCAD simulation of this triple junction solar cell. So this process involved solving many challenges like improving the current flow and making efficient tunnel junctions as well. We will break down the 17-layer structure of this triple junction solar cell and explore how each layer plays a role in the in this, you can say, groundbreaking device. So let's get started. Here is the code for the triple junction solar cell. We start with Go Atlas. And then I'm using a multiplication factor of 1 for this code. You can also use other multiplication factors for both x and y directions, or you can have a multiplication factor for just one direction as well. And then here I have defined the meshing in the x direction. The device runs from 0 to 1 micrometer in the x direction, and it runs from 0 to 3.330 micrometers in the y direction. And I've already run the simulation of the code under thermal equilibrium. So from this structure you can see that the device is running from 0 to 1 micrometer in the x direction and from 0 to 3.3 micrometers in the y direction. And then in order to see the meshing, I'm going to right click on this structure, click on this icon, hit apply, click OK. So now you see that I have defined denser meshing in the crucial layers, which are also really thin layers, and I have defined sparser meshing for thicker layers, and that is the strategy that we generally implement for pretty much almost all kind of devices. Going back to the code, so I'm not going to go into the depth of the meshing. It's a simple process, and I've already explained it in a lot of other Silvaco TCAD simulation based codes. Also, I want to add here that previously I have run the simulations of single junction solar cells, and I've also posted a video on the Silvaco TCAD simulation of double junction solar cell. So if you are not familiar with the single junction and double junction so far, I would definitely recommend watching those videos first and then turn to this video, because triple junction is much more complicated as compared to the single and double junction solar cells. Now we define each and every individual layer. Region number 1 is indium gallium phosphide based. It's running from 0 to 1 micrometer in the x direction and from 0 to 0.011 micrometers in the y direction. So region number 1 has a thickness of 11 nanometers, and it has an X content of 85%. And let me go back to the scheme for ternary alloys. Talking about indium gallium phosphide, as you can see over here, the X content over here actually represents the percentage of gallium in the ternary alloy. So here in region number 1, my X content is 85%, which means that this ternary alloy, indium gallium phosphide, has 85% of gallium and 15% of indium. And also I have defined these parameters in this layer number 1 as well. So layer number 1 is indium gallium phosphide based with 85% gallium content. Its thickness is 11 nanometers, and also it is p-type doped. I will define the doping later. Over here for region number 1, it's p-type, and the doping is 8 into 10 to the power of 18 per centimeter cube. If you go to the structure here, also here we can right click on the structure, go to display, and then click on this icon so that we can see the cathode and anode as well. So the top layer is anode and the bottom layer is cathode. And since the top layer is anode, the first layer that I have introduced over here is p-type, so that it can make a better contact with the top layer. So the indium gallium phosphide layer is really thin. As you can see over here, it's running from 0 to 0.011 micrometers. It has a thickness of 11 nanometers. Let me tell you about the top layer. So this top layer actually, in fact, let's go to the structure over here. We call it the window layer because it protects the cell from surface recombination and external damage while allowing maximum light to pass through to the second layer, which is the emitter layer. So basically it serves two purposes. It's transparently conductive, and it allows maximum light to pass to the rest of the device, and that's why we call it the window layer. Region number 2 is indium gallium phosphide based. Its gallium content is 46%, and it runs from 11 nanometers to 60 nanometers. So the thickness of region number 2 is 49 nanometers, and its doping concentration is defined here. It's 2.5 into 10 to the power of 18 per centimeter cube. So going back to region number 2. Now region number 2 is called the emitter layer. It is a highly doped layer that separates photo-generated electron-hole pairs and adds efficient charge carrier collection. Similarly, region number 3 is also indium gallium phosphide based. It runs from 60 nanometers to 610 nanometers, and its gallium content is 46%. We can also see it in the layer structure diagram over here. Its thickness is 550 nanometers, and we call it the base layer. It absorbs photons from the visible spectrum and generates the majority of the current for the top cell. So also I want to add that we have got 3 cells over here. Cell number 1 is based on indium gallium phosphide emitter and base layers, and the top cell actually absorbs shorter wavelength light, for example blue light. Similarly, the middle cell is based on gallium arsenide emitter and base, and it has a tendency to absorb red, near infrared light. Similarly, the bottom cell is based on indium gallium arsenide with a gallium content of 75% and indium content of 25%, and this cell is going to absorb light in the near infrared to the infrared wavelength range. Also, region number 3 is N-type doped, as you can see over here, and also in the definition of the doping, we see that region number 3 is N-type doped, and it has a carrier concentration of 8 into 10 to the power of 17 per centimeter cube. Similarly, region number 4 is indium gallium phosphide based. It has an indium content of 85%, and it runs from 610 to 730 nanometers, and its doping concentration is 4 into 10 to the power of 18 per centimeter cube N-type. We call it the base surface field layer. It reduces the carrier recombination at the back of cell number 1. Why do we call it the back surface field? Because this layer is actually found at the back of cell number 1, and it reduces carrier recombination at the rear end of the top cell, pushing the generated carriers back into the active region. So if we further look at the bandgap engineering of this layer, it actually facilitates electrons to transfer to the next cell, or to move to the next cell, and it actually pushes holes back into the cell so that the holes can actually move to the top electrode, which is the anode. Then region number 5 is aluminum gallium arsenide based, and also I'm going to show you the scheme for aluminum gallium arsenide as well. So here is the scheme for aluminum gallium arsenide. The X component in aluminum gallium arsenide corresponds to the aluminum content in this ternary alloy. So then if we go to region number 5, 98% means that it has this aluminum gallium arsenide has 98% of aluminum and 2% of gallium in this ternary alloy. And similarly, region number 6 is indium gallium phosphide based with a gallium content of 20%. Both of these layers have thicknesses of 10 nanometers each. Region number 5 is N-type doped with a carrier concentration of 7 into 10 to the power of 19 per centimeter cube, And similarly, region number 6 is 10 nanometer with the whole concentration of 1 into 10 to the power of 19 per centimeter cube. And these two regions, 5 and 6, actually comprise tunnel junction 1 connecting cell number 1 to cell number 2. Region number 5 forms the inside of the tunnel junction, providing high conductivity for electrons. Similarly, region number 6 completes the tunnel junction by forming the p side. Together, these layers ensure smooth charge flow between the top and the middle cells. Region number 7 is indium gallium phosphide based with a gallium content of 15%, and it has a thickness, it's running from 750 to 820 nanometers. It has a thickness of 70 nanometers, and it's p-type doped with whole concentration of 5 into 10 to the power of 18 per centimeter cube. It forms the window layer for cell number 2. So similar to the top cell, this window layer actually minimizes recombination and allows light to pass through to the emitter layer of cell number 2. Then similarly, region number 8 and 9 form the emitter and base layers for the gallium arsenide based solar cell. So region number 8 is based on gallium arsenide. Similarly, region number 9 is based on gallium arsenide. Region number 8 has a thickness of 100 nanometers, while region number 9 has a thickness of 1.6 micrometers. Region number 8 is the emitter layer, separating photon-generated carriers and enhancing charge collections for photons in the mid-spectral range. Similarly, region number 9 is the base layer. It is a thick layer that absorbs reddish light or near infrared light, generating most of the middle cell's current. Region number 10 is based on aluminum gallium arsenide, having an aluminum content of 70% and a gallium content of 30%. It has a thickness of 115 nanometers, and it's n-type doped with the carrier concentration of 5 into 10 to the power of 18 per centimeter cube. And it serves as the back surface field for cell number 2, ensuring efficient carrier collection by reflecting holes back and facilitating electrons to move to the next cell. And it also prevents recombination. Similarly, regions 11 and 12 form tunnel junction 2, connecting cell number 2 to cell number 3. These two layers have thicknesses of 15 nanometers each. Region number 11 is n-type doped with carrier concentration of 7 into 10 to the power of 19 per centimeter cube, and region number 12 is p-type doped with the carrier concentration of 1 into 10 to the power of 19 per centimeter cube. Region number 11 forms the N side of the second tunnel junction, enabling smooth charge transfer, while region number 12 completes the P side of the second tunnel junction, providing high conductivity for hole flow between the cells. Now let's turn to cell number 3. Region number 13 is actually the window layer for cell number 3. It's based on indium gallium phosphide with the gallium content of 70%. It's running from 2.665 to 2.730. So it has a thickness of 65 nanometers and a hole concentration of 3 × 10⁻18 per centimeter cube. And region number 13 reduces recombination losses, and it allows photons to pass through to the emitter layer in the bottom cell, or cell number 3. Region number 14 is based on indium gallium arsenide, and with the indium content of 75%. Let me show you the configuration for indium gallium arsenide. So in indium gallium arsenide, it's the other way around. So in indium gallium arsenide, the X component represents the gallium content, which means that in cell number 3 for this indium gallium arsenide, we have a gallium content of 75% and indium content of 25%. Region number 14 has a thickness of 100 nanometers. It serves as the emitter layer for cell number 3, separating carriers and supporting current generation for the long wavelength photons. And similarly, region number 15 is also based on indium gallium arsenide with a gallium content of 75%, and region number 15 has a thickness of 200 nanometers, and it's N-type doped with a carrier concentration of 2 × 10⁻17 per centimeter cube. It's a relatively thicker layer as compared to the emitter layer to absorb infrared photons, maximizing current output from the bottom cell. Region number 17 is aluminum gallium arsenide based with aluminum content of 70%, running from 3.030 to 3.130. So which means that its thickness is 100 nanometers, and its electron concentration is 5 × 10⁻18 per centimeter cube. It can also be called as the back surface field for cell number 3, reflecting holes, or we can also call it the hole blocking layer. So it basically blocks holes reflecting it back so that the holes can continue their movement towards the anode, and it facilitates electrons to flow towards the cathode, towards the bottom layer. So it basically ensures optimal carrier collection especially at this part of the cell. Region number 17 is gallium arsenide based, and it has a thickness of 200 nanometers and an electron concentration of 1 × 10⁻18 per centimeter cube. It provides structural support and acts as the substrate for the entire solar cell stack. And similarly, we can see the structure over here as well. So basically, in this structure, at the top we have the anode, then we have the window. This is the window layer for the top cell. Sorry, the window layer is actually pretty thin, so we need to zoom in on this. So this is the window layer, and then this is the emitter layer this is the emitter layer for cell number 1. This is the base layer, bake surface field. Here is the tunnel junction between connecting cell number 1 to cell number 2. This is the window layer for cell number 2, emitter layer for cell number 2, base layer for cell number 2. Similarly, here is the back surface field for cell number 2. Once again, here is the tunnel junction connecting cell number 2 to cell number 3. This red region based on indium gallium phosphide is the window layer for cell number 3, and then we have indium gallium arsenide based emitter and base layers, and then finally we have the back surface field and the substrate layer for the entire structure. Here I have defined the top of the structure as the anode and the bottom of the structure as the cathode, which we can also see in this Tony plot. The top layer is anode and the bottom layer is cathode. I saved the structure, then I start running another block of Atlas, and here I import the structure that I already saved in the previous block. Here I define the doping concentrations for the 17 different layers of this triple junction solar cell. In this block of the code, I actually define different material properties. For example, for gallium arsenide, indium gallium arsenide. Indium aluminum gallium phosphide is not part of the solar cell, but actually it does not really matter. But I initially included it. I was trying different window layers, including indium aluminum gallium phosphide. But at the end of the day, indium gallium phosphide worked better for me, so we don't really need to include this part. But it's okay. Maybe I may need to use it in 4-junction solar cell. Similarly, I've included aluminum gallium arsenide, indium gallium phosphide, and germanium is not part of this structure, but for a 4-junction solar cell, we would definitely like to add another cell, or you can call it cell number 4 at the bottom of the structure, making it a 4-junction solar cell. Now, if you focus on the material properties, we actually see the SOPRA command. In Silvaco TCAD, SOPRA files are used for defining the optical properties of materials, which is crucial for simulating solar cell. Because in solar cells, the input is light and the output is voltage and current. So the incident light on the solar cell actually has some properties related to light, or you can say optical properties. Every material is going to have refractive indices and absorption coefficients, which will depend on the wavelength of the incident light. So basically, the refractive indices and the absorption coefficients, they vary with the wavelength of the spectrum. So these SOPRA files typically include information. For example, here is the SOPRA file for gallium arsenide, and these files typically include information about the refractive index and absorption coefficient as a function of the wavelength. In Silvaco TCAD, these files are used to accurately model the optical behavior of the materials used in solar cells, and this is essential for simulating the absorption of sunlight within the semiconductor layers of the solar cell, which directly affects its efficiency as well. So for a lot of materials, for example, gallium arsenide, and also for indium gallium arsenide, Silvaco TCAD has built-in SOPRA files. But for some materials, for example, for indium gallium phosphide, here is indium gallium phosphide, and also for aluminum gallium arsenide, we generally don't really have the SOPRA files. In fact, so we have the SOPRA file for indium gallium phosphide. We don't have it for indium gallium phosphide. So for a lot of materials, we do have the SOPRA files. So wherever you see the SOPRA command, we actually have SOPRA files for these materials. We have it for gallium arsenide. We have it for indium gallium arsenide, we have it for indium aluminum gallium phosphide, we have it for germanium as well. However, for some materials including indium gallium phosphide, we don't have the built-in Sobra files in Silvaco TCAD. So what do we do in that scenario? In that scenario, we need to create a file which should have the refractive indices and also the absorption coefficients information related to that particular material. And I basically have created a file for indium gallium phosphide. I'm going to show it to you. So this is the file, and basically this 1000 over here actually corresponds to we have 1000 entries in this file. Then we have 3 columns. The first column over here corresponds to the wavelength, and the second column corresponds to the refractive indices, and the third column corresponds to the absorption coefficients of these materials. So the wavelength is running from 0.2, scrolling down to 1.2 micrometers, and for each value of the wavelength we have corresponding refractive index and absorption coefficient value. So I have created that file, and I'm actually calling that file using index.file command so that I can call it into this code. And then this file is actually named as indium gallium phosphide.nk. So I have defined material properties for all these materials. Similarly, I have defined the electron affinities for these materials. Then I've included different models for the simulation of the triple junction solar cell structure. Several different numerical methods can be used for calculating the solutions to semiconductor device problems. Basically, there are 3 types of solution techniques: Gummel, Newton, and Bloch. And here I'm using Newton method for the solution, numerical solution of this solar cell structure. Here I want to output different parameters for this solar cell structure: conduction band, valence band, charges, polarization charges, band parameters, electron and hole mobilities, Shockley-Red-Hall recombination, radiative, OJ recombination, etc., permittivity, etc. In this part of the code, solve initial and solve previous actually give us an initial guess of the structure. So here I'm actually running the structure under thermal equilibrium, and this figure that you actually see over here is actually under thermal equilibrium. And we can also see it from the energy band diagrams that I'm going to show it to you later. Then in this block, I want to see the IV characteristics of this triple junction solar cell under dark conditions. So I'm basically creating a log file with this name, and then I'm running a voltage sweep from 0 to 2.4 volts with a step of 0.02 volts. And then I use this command to hold the log file as for now, because I want to run the IV characteristics of the solar cell under light conditions as well, and then I want to plot the IV under dark and light conditions into the same figure. So that's why I'm using this log off, so that I can hold onto this log file as for now. Then I want to simulate the IV characteristics of the solar cell under light conditions as well. The solar spectrum typically extends from the infrared to the ultraviolet region from approximately 0.2 to 3 micrometers. And the problem is that the intensity is not uniform. Now, we actually run this simulator. I'm running this simulation under AM 1.5 G conditions corresponding to diffuse light. Now, what is AM 1.5? So basically, the path length of light in the atmosphere depends on the angle, which will vary with the time of the day. And this is given by AM, air mass, or you can call it the air mass number, which is the secant of the angle between the sun and the zenith, or you can say between the sun and the vertical angle. So AM0 would represent the solar spectrum outside the Earth atmosphere. Similarly, AM1, which is we see AM1 when the angle is 0. Similarly, AM2 when the sun is at an angle of 60 degrees. Similarly, AM 1.5 when the sun is at an angle of 48.2 degrees to the vertical angle. So AM 1.5 corresponds to that scenario in which the sun is actually at an angle of 48.2 degrees to the vertical angle. And why exactly this angle? Because generally we simulate the solar cell under standard test conditions, which means an irradiance level of 1000 watts per meter square, or you can call it the light intensity as well. And 1000 watts per meter square corresponds to 100 milliwatts per centimeter square. Similarly, this is one part of the standard test conditions, 1000 watts per meter square. Similarly, we under standard test conditions, we simulated under AM 1.5 spectrum, and at a temperature of 25 degrees corresponding to 77 degrees Fahrenheit. So these conditions allow manufacturers and consumers to make direct comparisons between different solar cells, ensuring that performance metrics like efficiency and power output are measured under consistent and reproducible conditions. Now, the next step in solar cell analysis is to illuminate the device. And we can turn on the illumination by assigning the beam intensity on a solve statement. This statement over here. As we had assigned AM 1.5 on the beam statement over here, this corresponds to standard test conditions. However, if we directly apply an intensity of one sun, which corresponds to 1000 watts per meter square, in some cases we may encounter convergence difficulties with the solution method, and we may need to ramp up the light intensity as shown over here. So we gradually increase it to 1 watt per meter square, then 10 watts per meter square, then 100 watts per meter square, and then finally to 1000 watts per meter square. This one over here corresponds to one sun. If you want to simulate concentrating solar cells, you can make it like 2, 10, 100, etc. But for this simulation, we want to simulate it under one sun, 1000 watts per meter square, or we can call it 100 milliwatts per centimeter square. And now the next step is to extract the illuminated forward IV characteristic. So for that, the first thing we need to do is to create an output file for capturing the data. And this is the log file that we created. Just to make myself famous, I'm including my own name, but I mean, you can definitely vary there. So this specifies that all the IV characteristic extracted from the solve statement will actually be captured into this log file in the current working directory. And then we run a sweep for the voltage from 0 to 2.4 volts under light condition. Just want to make sure that the voltage range and steps are the same under dark and light conditions, so they are the same. And then we use the command of overlay in order to plot both the IV characteristic under dark and light condition in the same figure. Here I'm saving the structure under light conditions as well, so that we can look at photon generation rates, photon absorption rates, that kind of stuff. And then I call this log file under light conditions once again, so that I can extract some parameters. For example, the short circuit current density from here. We see the short circuit current density where the X value on the IV characteristic is 0. So basically the X intercept of the IV characteristic. And then in order to convert it into short circuit current density in milliamps per centimeter square, we multiply the short circuit current density with the area of the device. So if you look at this device, it's running from 0 to 1 micrometer in the X direction, and actually the light is going to be incident over here at the top. Then if we call this the Z direction, this is the Y direction. So if we call the third dimension the Z dimension, I've not introduced it, but by default the Z dimension is 1 micrometer. So it means that the top surface area of this device is 1 micrometer by 1 micrometer. And we know that 1 micrometer is 10 to the power minus 4 centimeter. We want to see the current density in milliamps per centimeter square. So 1 micrometer by 1 micrometer would be 10 to the power of 8. So for current density, we divided by the area. So it's going to be like JSC divided by 10 to the power minus 4 into 10 to the power minus 4. Take it to the numerator, it becomes 10 to the power minus 10 to the power of 8. And similarly, we want to see the current density in milliamps per centimeter square, so multiply it with 1000. Then we want to see the open circuit voltage at the y-intercept of the IV characteristic. Then we want to see the power curve, which is going to be a multiplication of the anode current versus the anode voltage. We find out the maximum power point in the power curve and also the maximum voltage point. Similarly, we want to see the fill factor, V maximum, I maximum divided by VOC into JSC into 100. And similarly, the efficiency is the output power, V maximum times I maximum divided by, this is the light intensity, 100 milliwatts per centimeter square, into area. Area is 10 to the power minus 8 centimeter square. Take it to the numerator, it becomes 1 10 to the power plus 8 multiplied with 100, and that is going to give us the efficiency. And then we plot the power curve here as well. So now that we are all set, I'm going to run the simulation, and this is going to take some time because it's quite a detailed structure. The structure is already simulated under thermal equilibrium. Right click on the structure, go to display, and click on this icon, hit apply, click OK. Now we see the anode and the cathode. Similarly, right click on the structure once again, go to display, click on this icon. We can see the meshing now, where for example here is my tunneling junction, so I want like denser meshing in the tunneling junction. Also I want denser meshing in this region as well. This is my second tunnel junction connecting cell number 2 to cell number 3, so you can see we have got denser meshing in thin layers and sparser meshing in thicker layers, as you can see in this base layer of the gallium arsenide cell, which is the middle cell. Similarly, right click, go to display, disable the meshing, and then we can also see the doping profiles of this structure. So right click, go to display, click on contours, go to define, click contours once again. Absolute net doping is fine, but you can also see a lot of other parameters. Hit apply and click OK. So this gives you the doping profile of your entire structure, as you can see over here. From here we can see that the emitter layers have relatively higher doping as compared to the base region in cell number 1, cell number 2, and also in cell number 3. We can also go to tools, cut line, draw a cut line across the entire structure, and then left click on this figure and then go to delete. Then right click over here, go to display. To disable the stars, I click on this icon, hit apply. This gives you the doping. So as you can see that we've got relatively lower dopings in the base regions, base region of cell number 1, cell number 2, and cell number 3 as compared to the emitter regions. And also the dopings are higher. This is tunnel junction 1, this is tunnel junction 2. The dopings are much higher in the tunnel junctions as well. Similarly, we can see the band gaps. Click apply. So over here we can see that the window layer of the top cell has a wider energy band gap. Similarly, the base surface fields of all the 3 cells have wider energy band gaps. Similarly, another crucial thing that you actually want to see is the top cell has the widest band gap, which means that it's going to absorb the shortest wavelength lights. Then the middle cell has a relatively lower band gap as compared to the top cell. So it means that the middle cell is going to absorb medium wavelength light, and the bottom cell, or the cell number 3, has the smallest band gap, which means that it's going to absorb the longest wavelength light for the solar spectrum. Also, right click on this once again, go to display, click on EC of T, EV of T, electron QFL, and hole QFL, hit apply. This gives you the energy band diagram of the entire structure under thermal equilibrium. So once again you can see that the top cell has the widest energy band gap, the middle has medium energy band gap, and the bottom cell has the smallest energy band gap out of the 3 cells. I'm gonna close this figure and see the progress of the simulation so far. So we are actually at the illumination phase, and this simulation is going to take some time. I'm gonna close the other figures. For example, this one is okay, we can still leave it here. So as I already told you that the simulation is going to take some time, so let's keep watching it, and I will discuss it once again once it runs the simulation under dark and under it already did the simulation under dark conditions. So now it's running the simulation under light conditions. So once it runs the sweep for the IV characteristic under light condition, we will reconvene talking about the results once again. So now as you can see that it has started running the sweep from 0 to 2.4 volts. Right now it's around 0.72, 74, 76, 78, 80, 0.84, 86, 88, 0.90 volts. So it's running the sweep now. It's done running the sweep. So we can see, for example, here is the simulated structure now under illumination, and this window is giving me some trouble. Okay, so I right click on the structure, go to display, and then click on contours, go to define, click on contours once again, and I want to see the photo generation rate of this structure. Here it is. Hit apply, click on OK. So now you can see the photo generation rate of this structure under illumination, and once again you can see like where the photo generation is high and where it's low. What we can do is go to tools and then click on cut line and draw a cut line across the entire structure. Left click on the left figure, delete that one, and here I wanna disable the stars, so hit apply. So now here you see the photo generation rates of different layers inside the structure. As you can see, here is the photo generation rate of the window layer. So as you can see, the window layer is supposed to not absorb a lot of photons. So here the photo generation rate and the absorption rate is pretty low. Then you see that the first cell, here is the photo generation rate for the first cell, exponentially decreasing. Then the tunnel junction has a low photo generation rate. Then we go to the second cell, the photo generation rate is exponentially decreasing over here as well. Then we go to the third cell. So once again we have the photo generation rate. Now how did I design my structure? This actually seems to be not such a significant figure, but it actually is if you know the ins and outs of how to design a triple junction solar cell. It's not easy. Like, I've got 17 layers and I have to optimize the doping concentration and the thickness and the content, percent content of in ternary alloys. So it involves bandgap engineering as well. So 17 into 3, it becomes like 51 different variables. How are you going to play with 51 different variables? It's not easy. So you got to be smart as well. You need to know how each and every individual layer performs in terms of their absorption properties, and also but I mean, this figure is crucial, like how. So the way I optimize my structure, especially for the thicknesses, is okay, I assumed this not to be like an exponentially decreasing line. I kind of assumed it as a straight line. So then I was like, okay, it has got a base corresponding to thickness, and it has an altitude. So I assumed it to be a triangle. And then what is the area under the curve? So there's going to be this thickness times the value over here for the photo generation rate. So similarly I calculated it for this one, and similarly I calculated it for cell number 3. And then I tried to optimize the thickness in such a way that from all the 3 cells I get kind of similar areas under the curve in order to better optimize the design of this triple junction solar cell. And this part was really crucial, helping me to get the efficiency up to 31.5%. And like, honestly, I can still bring it up like further. In fact, I designed a triple junction solar cell for a party, and it has an efficiency of 35%. So then, but then I have to play around with the parameters once again, so that I'm not exactly replicating the same structure, but we have a room to bring this efficiency even further up by further optimizing the design parameters. But due to time constraints, I'm not further able to dedicate more time to it. Like it takes really long time to optimize this design. Then we can also right click on the structure, go to display. Instead of the photo generation rate, we can look at the energy band diagram of this structure under light conditions. So I click on ECFT, EVFT, electron QFL, and hole QFL. Hit on apply. A hole QFL, EVFT, electron QFL, ECFT. And then okay, so here is the energy band diagram of the structure under light conditions. And what else I want to see? So then I want to see IV characteristics of the structure under dark and light conditions as well. So I'm going to close this figure. Here are the IV characteristics of this structure under dark and light conditions. The green curve corresponds to the IV characteristic under light conditions. It's actually its x-intercept is around at approximately 2.4 volts, which corresponds to the open circuit voltage. And if you go to the device performance parameters, click on this icon, it's going to give you the output parameters. So from here we can see the open circuit voltage for this design is approximately 2.37, close to 2.4 volts. So this point, like we can see it on the figure as well. Furthermore, you can also export the IV characteristics under dark and light conditions. And I want to click this option which corresponds to comma separated values. I basically want to export it in Excel format. You can call this file IV dark and light, and then we need to select a folder. Click OK and click OK once again. It says export succeeded. So now we go to that corresponding folder. Here is that Excel sheet. In this Excel sheet, we can see like we have a column for the anode voltage, and then we have another column for the anode current as well. So from here you see the IV, you see columns for the voltage and for the current under dark and light conditions as well. And then you can just like you can plot them in origin, or you can plot them in any other platform as well. Similarly, here is the power curve for the triple junction solar cell, and this is the maximum power point. The maximum power corresponds to a maximum voltage of approximately 2.22 volts. We can see that in the performance parameters as well. Vm is equal to 2.22 volts, and here we see the short circuit current density is 14.43ish milliamps per centimeter square. The efficiency is 31.54%, and ignore the negative sign. It's all about like we have applied formulas here. So in these formulas, if instead like somewhere I've used a negative sign over here, if instead of the negative sign you use a positive sign, so it's going to give you efficiency of having positive value. So don't worry about the negative sign over here. And then the fill factor of this triple junction solar cell is 92%, which is really good fill factor, and that is obvious from this IV characteristic as well. It's pretty much vertical over here around the knee. So similar to the IV characteristic, also if you click on in the center of this icon, you can zoom out your characteristic curves. So similar to the IV characteristic, you can also go to File, Export, click on CSV, go to that corresponding folder, name this file, and you can export in an Excel format, and then later you can plot that in origin. So that pretty much winds up this session. To sum up, triple junction solar cells are an incredible advancement in solar technology. By stacking layers that absorb different parts of sunlight, they can achieve much higher efficiencies than single and double junction solar cells. However, designing these cells is not an easy task. Current matching between the layers, efficient tunnel junctions, and careful optimization of each layer's properties are all critical in order to be successful for optimal design of this triple junction solar cell. Using tools like Silvaco TCAD, researchers can simulate and refine these structures to push the limits of the efficiency. Achieving 31.5% efficiency is the result of precise engineering and countless iterations, as we have already seen, of testing and improvement. If you found this breakdown helpful, don't forget to like, subscribe, and leave a comment with your thoughts or questions. Thank you for watching, and I will see you in the next video. Take care. Adios.